Look at it. A perfect grid of concrete and asphalt built to facilitate movement. Yet, here we are. A tableau of stalled metal, engines idling in the heat haze, time measured by frustration.
This intersection, designed for efficiency, has become a monument to delay. We have invested billions into these arteries, the overpasses, the traffic signals, the sheer scale of modern American infrastructure.
And yet, during peak hours, the flow often feels less like a system and more like a chaotic collision of individual wills.
It is a paradox. A massive network built for optimal motion that frequently generates profound inefficiency. What governs this colossal ballet of metal? Is it simple timing, or something far more complex?
We are about to investigate the invisible intelligence, managing the rhythm of an entire metropolis.
Early traffic control was a triumph of mechanical simplicity. The first signals were purely fixed-cycle devices. Timers set to repeat predictable sequences regardless of actual demand.
They operated on the assumption that traffic flow followed rigid, unchanging patterns. This approach worked adequately for smaller towns and stable periods.
But as American cities swelled in population and vehicle ownership exploded, these basic timing cycles faced insurmountable limitations.
A signal optimized for a morning rush hour might completely fail during an unexpected afternoon surge or a sudden detour.
The system lacked the ability to see what was happening moment by moment, forcing engineers to constantly guess at future conditions based on historical averages.
This fundamental constraint created the urgent need for real-time data input, a shift from simple timing to true network intelligence.
The breakthrough required not just better programming, but a complete overhaul of the system's sensory input. The modern traffic control grid operates on an invisible layer of continuous data collection.
High-definition cameras mounted at every corner capture everything from vehicle count to queue length. Embedded in the asphalt are induction loops, simple electrical circuits that detect the precise presence and passage of tires.
Complementing these are advanced radar sensors, which measure speed and density across wide swaths of roadway.
These technologies work together, collecting massive streams of raw data points, a constant stream detailing every vehicle's location, its speed, and its immediate trajectory within a monitored intersection.
This continuous flow transforms the physical road into a dynamic, measurable dataset, providing the foundational intelligence needed for true network coordination. This deluge of information is immediately processed by central computing units. Algorithms analyze.
This computational layer is where the magic happens, the brain of the system. Gone are the days of fixed cycles, where every intersection operated on a rigid, pre-programmed schedule regardless of need.
Modern signal optimization algorithms ingest that continuous stream of data and perform real-time predictive modeling. They don't just react to traffic, they anticipate it. By analyzing historical patterns alongside immediate demand, the sudden surge from an event or the predictable morning commute, these sophisticated programs dynamically adjust green light durations across entire corridors.
The goal is maximizing network throughput while minimizing wasted time for every single vehicle, effectively turning a collection of separate lights into one cohesive, breathing circulatory system that breathes with the rhythm of the city itself.
This predictive capability allows for coordinated green waves. A seamless flow that guides vehicles through multiple intersections without stopping. It's a symphony.
The true genius of traffic management lies not at isolated corners, but along entire arteries. These major corridors are treated as single, continuous conduits, the network effect in action.
Instead of managing individual stops, the system aims to manage momentum. It must predict and sustain a wave of vehicles moving for miles down an avenue.
This requires sophisticated synchronization, creating what is known as a green wave. A green wave isn't just a sequence of lights. It's a choreographed passage that guides traffic through multiple intersections without requiring a single stop.
The goal is continuous flow, a sustained rhythm that maximizes the throughput capacity of the entire street segment. It transforms a collection of separate reactive signals into one cohesive, proactive circulatory system. Engineers fine-tune these timings using complex algorithms, adjusting for real-time demand, be it rush hour congestion or weekend leisure traffic.
But this seamless coordination is not magic. It is the product of rigorous human intelligence and computational modeling.
Before a single line of code can be deployed to a physical signal, planners build sophisticated digital twins, virtual replicas of entire city grids.
These models allow engineers to test countless scenarios. What happens if an accident blocks a lane? How does increasing the cycle time at one corner affect flow 3 miles down the road?
By simulating millions of vehicle movements and pedestrian patterns, they can predict bottlenecks and optimize timing with unprecedented accuracy. However, no digital model is perfect.
The reality of unique geography, a sudden river crossing, a historical district's narrow streets, demands constant human adaptation, turning theoretical efficiency into practical urban flow. These real-world variables, from unexpected construction to seasonal crowd surges, require iterative adjustments.
Planners must constantly recalibrate algorithms, ensuring that theoretical.
But even the most sophisticated network is vulnerable. A power grid failure, a sensor malfunction, or an unforeseen physical obstruction can throw the entire choreographed ballet into chaos.
The question then becomes, how does the system fail gracefully? Modern traffic infrastructure is designed not just for peak efficiency, but for resilience. These built-in redundancies are critical safety nets.
When central communication fails, local controllers revert to basic, pre-programmed timing cycles, a safe, predictable pattern that maintains minimum function.
This isn't a graceful failure, it's an engineered fallback, ensuring that while the optimal flow is lost, complete systemic collapse is prevented. It trades perfect synchronization for guaranteed movement.
For instance, many intersections default to fixed time intervals. A simple, reliable sequence of green, yellow, red. This manual fallback ensures that even without digital input, vehicles can continue moving through established patterns until power is restored and coordination resumes.
The current system, while robust in its redundancy, still operates on a reactive model, a series of localized decisions made at each intersection. The true evolution lies in predictive intelligence.
Imagine a city where every vehicle, from the private sedan to the public bus and the emergency ambulance, is constantly communicating with the infrastructure itself.
This V2I communication creates a single, dynamic operating picture for an AI manager.
Instead of managing lights, this system manages flow optimizing speed, predicting congestion points minutes in advance, and dynamically assigning right-of-way based on real-time need. The goal isn't just efficiency, it's seamless integration.
In the most advanced future grids, traffic signals may become obsolete entirely, replaced by invisible digital orchestration that guides every movement into a single, optimized stream of urban mobility.
This digital orchestration moves beyond mere timing adjustments. It anticipates human behavior, prioritizing.
So, what we are witnessing is not merely a series of timed lights, but an intricate, continuous dialogue between data and physical reality.
The entire system operates as a massive distributed nervous network, constantly sensing flow, predicting congestion, and adjusting signals in milliseconds.
This invisible choreography, the seamless ballet of millions of vehicles every hour, is driven by algorithms that ingest real-time inputs from sensors, cameras, and GPS trackers across the grid.
It is a monumental feat of engineering intelligence, transforming raw data into fluid urban movement.
The result is a city that appears to breathe with perfect rhythm, a complex machine operating at peak efficiency, proving that even the most mundane infrastructure can house profound technological sophistication. This constant optimization minimizes idling time and fuel waste across thousands of intersections daily. It is a silent testament to predictive computing, ensuring that